In the last video, we opened up attention and looked at every part of it. A query, a key, a value, a dot product, a scale, a softmax, a weighted sum, and at the end of it, one line of arithmetic that turned out to be the engine of the entire field, but we left something on the table. We showed you how attention works. We did not really deal with what it costs. Here is the cost, and it is not subtle. Attention lets every token look at every other token. That is the whole idea. But if you have n tokens and each one looks at all n of them, then you have to compute n times n scores. The work does not grow with the length of your text. It grows with the square of it. Put real numbers on that. At 512 tokens, which is what the original paper trained on, you are filling in about 260,000 cells. Double the input to 1,000 tokens and you do not do twice the work, you do 4 times. At 4,000 tokens, you are at 16 million cells. At 100,000 tokens, 10 billion. At a million tokens, a trillion. And every one of those numbers has to be held in memory at the same time, because the softmax needs the whole row before it can normalize any of it. So here is the gap this video is about. In 2017, the transformer trained on sequences of 512 tokens. Today you can hand a model a million tokens and it will answer. That is a factor of 2,000 in length, which means a factor of 4 million in raw attention work. Hardware got faster over those years, but it did not get 4 million times faster, so something else had to happen. This video is the story of that something else, 10 years of it. We will watch the field try to make attention cheaper by approximating it, and watch that fail on a benchmark that nobody wanted to publish. We will watch a graduate student point out that the whole community had been optimizing the wrong thing. We will watch the bill move from training to serving, and watch an entirely different architecture appear that throws attention out completely, and then watch the two ideas turn out to be the same idea in disguise. And we will end in 2026 with an honest answer to the question everybody asks, which is whether the quadratic problem was ever actually solved. The first reaction to a quadratic cost is the obvious one. If you cannot afford every pair, do not compute every pair. Between roughly 2018 and 2021, something like 100 papers took a run at that idea. They are usually listed as a soup of names, but they are not 100 separate ideas. They are about 6, and once you can see the 6, the whole period makes sense. The first family is fixed patterns. Decide in advance which cells of the grid you will bother to fill in and leave the rest empty. The sparse transformer from OpenAI in 2019 used strided bands, so a token attends to a fixed stride of previous tokens plus its immediate neighbors. Longformer in 2020 used a sliding window, so every token sees a fixed number of tokens either side of it, plus a handful of global tokens that everyone can see and that can see everyone. Big Bird added random connections to the window and the global tokens, and proved that the combination is still, in theory, as expressive as full attention. The second family is learned patterns. Rather than fixing the sparsity in advance, work out at runtime which pairs are worth computing. Reformer did this with locality-sensitive hashing. Vectors that point in similar directions get sorted into the same bucket, and you only compute attention inside a bucket. The appeal is that the model discovers its own sparsity. The problem is that hashing is a lot of bookkeeping, and bookkeeping is exactly what graphics processors are bad at. The third family gives up on sparsity entirely and attacks the shape instead. Linformer observed that the attention matrix is, in practice, close to low rank, which is a technical way of saying it contains far less information than its size suggests. So project the keys and values down from n rows to a fixed k rows before you ever compute the scores. Your matrix is now n by k instead of n by n, and k does not grow with the input. That is genuinely linear. Fourth family is the most mathematically elegant, and it turns on a piece of algebra. Attention computes softmax of q times k transpose and then multiplies by v. The problem is the softmax in the middle, because it forces you to build the n by n matrix before you can go any further. But if you could replace the softmax with something that factorizes some feature map applied to q times the same feature map applied to k, then the brackets move. Instead of q by k by v, you compute k by v first, which is small, and then q by that. The n by n matrix never exists. That is the linear transformer and performer, which approximates the exponential with random features. So that is the map: fixed patterns, learned patterns, low rank projection, kernel factorization. Add downsampling, which just shortens the sequence, and recurrence, which carries a summary between blocks, and you have essentially all of it. Every one of these methods works. Every one of them delivers the complexity it advertises. The question the field had not yet asked was whether any of them were actually any good. By 2020, this was a real problem for the literature. Every paper reported that its method was faster than the transformer and comparable in quality, but they all tested on different tasks at different lengths with different budgets against different baselines. Nobody could say which of them was best, or whether any of them were better than doing nothing clever at all. So a team at Google Research built a benchmark specifically to settle it and called it Long Range Arena. 6 tasks, all requiring genuinely long context, classifying long documents, matching 2 long documents for similarity, parsing deeply nested mathematical expressions. And the hardest one, called Path X, where the model is given an image flattened into a sequence of 16,000 pixels and has to decide whether 2 dots are joined by a path. Every model got the same budget, the same data, the same evaluation. Then they ran 10 efficient transformers through it, and they ran the plain original transformer through it too, as a control. The plain transformer scored 54.39. Of the 10 efficient variants, 9 scored below it. Big Bird at 55.01 was the only one above, and it is above by 0.6 of a point. Reformer scored 50.67. The linear transformer scored 50.55. 3 years of work on making attention cheaper, and the honest summary was that making it cheaper made it worse, and mostly not even much faster in wall clock terms once you accounted for the overhead. And there was a detail in the table that was worse than the averages. On Path X, the hardest task, every single model failed, not scored poorly. Failed. Every one of them landed at chance, which on a 2-way decision means 50%, which means none of them had learned anything at all. The benchmark had a task that no attention-based model of any kind could do. Hold on to that, because in about 20 minutes something is going to solve it. It would be easy to read Long Range Arena as a verdict that the whole efficiency project was wasted and that reading is common. It is also wrong, and the next chapter is about why, but the benchmark did do one thing decisively. It ended the era in which you could publish a faster attention mechanism, report that quality was comparable, and be believed without evidence. From 2021 onward, the burden of proof moved. Here is the part of the story that usually gets left out because it complicates a clean narrative. The benchmark said these methods were worse on average. The industry shipped several of them anyway and is still shipping them today. Both of those things are true, and the tension between them is the interesting bit. Start with the sliding window from Longformer. A token attends to a fixed number of tokens on either side and nothing else. In 2020, that was an efficiency paper. Today, it is simply part of how models are built. Mistral shipped it. Gemma shipped it. And when OpenAI released the weights of an open model in 2025, its architecture alternated between banded window layers with a bandwidth of 128 and fully dense layers. Not as an efficiency hack bolted on afterwards, but as the design. The strided and banded patterns from the sparse transformer had already gone further than that. They were in GPT-3 in 2020, which alternated dense and locally banded sparse attention through its layers. So the single most influential model of that era was already, quietly, running a sparse attention pattern from an efficiency paper, while the benchmarks were reporting that sparse attention underperformed. And Linformer, which Long Range Arena ranked near the bottom, went into production at Meta in November 2020, serving real traffic, not as a research demonstration, as infrastructure. So what actually happened? The benchmark measured one thing, which is whether these methods can replace full attention across the board without losing quality. The answer to that was no. But industry was asking a different question, which is whether a cheap approximation is good enough in the particular layers, at the particular lengths, and for the particular workload you actually have. And the answer to that was frequently yes. The pattern that survives is not the general purpose replacement. It is the local window used alongside full attention in some ratio. Keep that shape in mind. We are going to watch the entire field converge on it twice from two completely different directions. In 2022, a paper came out of Stanford that reframed the entire problem, and it did it by pointing out that everybody had been counting the wrong thing. Its argument is that attention was never limited by arithmetic. It was limited by memory traffic. And once you believe that, almost everything that came before looks like it was solving a problem that was not the bottleneck. The argument, you have to look at what a graphics processor actually is. There are three tiers at the top: a small pool of on-chip static memory measured in tens of megabytes running at something like 19 terabytes per second. Below it, the high bandwidth memory on the card, tens of gigabytes running around 2 terabytes per second. Then ordinary system memory, far larger and far slower again. Roughly an order of magnitude of bandwidth between each tier, and about 3 orders of magnitude of capacity in the other direction. The arithmetic units live at the top, everything else is a journey. Now trace what standard attention actually does. It computes Q times K transpose, and that result is an n by n matrix, which is far too big for the fast memory, so it gets written down to high bandwidth memory. Then the softmax has to read all of it back up, normalize it, and write it back down again. Then the multiply by V reads it back up one more time. For a sequence of a few thousand tokens, you have just moved tens of gigabytes of intermediate data back and forth to do an amount of arithmetic that the chip could have finished in a fraction of the time. The processor spends most of the operation waiting. So the fix is not to make the matrix smaller. The fix is to never write it down. Load a block of queries and a block of keys into the fast memory. Compute that tile of scores right there. Immediately use it, immediately discard it, move to the next tile. The full matrix is never stored anywhere because it never needs to exist all at once. There is one obstacle, and it is the softmax. Softmax needs to subtract the maximum of the row for numerical stability, and it needs to divide by the sum of the whole row. Both of those appear to require seeing the entire row before you can produce any output. The trick that makes tiling possible is called online softmax, and it dates back to a short note from 2 engineers at NVIDIA in 2018. You keep a running maximum and a running sum as you go, and every time a new tile arrives with a larger maximum, you rescale everything you have accumulated so far by the appropriate factor. It is exact, not an approximation, not a bound. The same numbers computed in a different order. And that is FlashAttention. Exact attention, identical outputs, but 3 times faster on the models of the day, and with memory that grows linearly rather than quadratically, because the quadratic thing is never materialized. Notice what it did not do. It did not reduce the number of multiplications. It is still order n squared arithmetic. It just stopped moving the data. 3 years of the field trying to reduce the arithmetic, and the biggest single win came from someone who left the arithmetic completely alone and fixed the memory traffic instead. FlashAttention was not a paper that came out and settled the matter. It became a piece of infrastructure that gets rewritten every time the hardware underneath it changes. 4 generations in 4 years, and each one exists because a new chip arrived with a new thing to exploit. First version in 2022 established the idea. Tile the computation, keep the tiles in fast memory, use online softmax so the result is exact. Roughly 3 times faster on the models of the day, and memory that grows linearly instead of quadratically. The second version, a year later, was not a new idea. It was a confession that the first implementation was leaving most of the chip idle. It reorganized the work so that the expensive matrix multiply units stayed busy, and the cheap rescaling operations happened less often, and it split the work across the sequence rather than only across batches and heads, so that even a single long sequence could fill the machine. That alone roughly doubled it again. The third version in 2024 was written for NVIDIA Hopper generation, and it is a good illustration of how specific this work has become. Hopper has dedicated hardware for moving memory asynchronously, and it has units that can do matrix multiplication at very low precision. So version 3 overlaps the data movement with the arithmetic, so the chip is never waiting, and it handles 8-bit floating point carefully enough that the accuracy holds. You cannot write that code without knowing the chip intimately. And the fourth version for Blackwell is where it gets almost funny. It reaches something like 1.6 petaflops per second, which is a number that would have sounded like a supercomputer a decade ago and is now one accelerator running one attention kernel. Its main algorithmic change is a refinement of online softmax itself. The original rescales every time it sees a new maximum. Version 4 makes that rescaling conditional, so it only pays the correction when the correction actually matters, and that cuts the number of corrections by roughly an order of magnitude. Which is to say, in 2026, someone shipped an amendment to a 2-page numerical note that 2 NVIDIA engineers wrote in 2018. There is one more detail worth naming because it tells you what kind of field this is now. The code for version 4 was presented at a hardware conference in August 2025, roughly 6 months before the paper describing it appeared. The artifact came first. The publication was the follow-up. In most of science, that ordering would be strange. Here it is normal because the thing being contributed is not really an idea, it is a kernel that runs. Everything so far has been about training or about one forward pass. But somewhere around 2023 the center of gravity shifted, the expensive thing stopped being teaching the model and started being answering with it, millions of times a day. And when you look closely at what serving a model actually involves, you find it is not one workload, it is two, and they want opposite things from the hardware. The first phase is Prefill. You have the entire prompt in hand, every token of it, all at once. So you can process all of them in parallel as one enormous matrix operation. This phase is compute-bound, meaning the chip's arithmetic units are the limit, which is a good problem to have, because that is the thing accelerators are built for. Prefill is the phase where making the arithmetic cheaper actually helps. The second phase is decode, and it is a different animal entirely. You are generating the reply one token at a time, and each token depends on the one before it, so there is nothing to parallelize. For every single token you produce, you have to read the entire stored history of keys and values back out of memory. One token of arithmetic, gigabytes of reading. The arithmetic units sit almost completely idle while the memory bus does all the work. Decode is not compute-bound. It is memory-bound, and it is memory-bound by a wide margin. This is not a theoretical distinction. DeepSeek published the layout of their own production deployment, and the shape of it says everything. 32 graphics processors assigned to Prefill, 320 assigned to decode. Times the hardware on the phase that does less arithmetic, because that phase is starving for bandwidth rather than for compute. The industry now routinely runs these two phases on separate machines because they cannot be tuned to make each other happy. And that reframes the whole optimization problem. If decode is memory-bound, then the thing to shrink is not the number of operations, it is the thing you have to read. That thing is the key value cache, and for the next few chapters, almost everything is about making it smaller, or reading it less, or not paying for it twice. Here is the size of the problem. Multi-head attention stores a separate key vector and a separate value vector for every head, for every layer, for every token you have seen. Multiply those out for a large model with a long conversation, and the cache runs into tens of gigabytes. It is often larger than the model weights themselves. The first attempt at fixing this appeared in 2019 from Noam Shazir, and the idea takes one sentence. Keep all the query heads, but let them share a single set of keys and values. If you have 64 query heads, you go from 64 copies of the cache to 1. The paper was published, and then essentially nothing happened for about 3 years. It was too aggressive. Sharing one key value pair across every head costs you real quality, and in an era when nobody was serving models at scale, nobody was desperate enough to pay that price. By 2023, people were desperate enough, and the fix was the obvious middle, grouped query attention. Instead of 64 sets of keys and values or one, use 8. Each group of 8 query heads shares a set. You get most of the memory saving and almost none of the quality loss. And it came with a practical detail that mattered enormously for adoption, which is that you do not need to retrain from scratch. You can take an existing checkpoint, average the key and value projections within each group, and continue training for something like 5% of the original pre-training compute. That turned it from an architecture decision into an upgrade. Within about a year, it was the default almost everywhere. The third step from DeepSeek in 2024 is more interesting than either. Instead of sharing heads, compress them. Project the keys and values down into a single low-dimensional latent vector and cache only that. When you need the actual keys and values back, reconstruct them on the fly, and because the reconstruction is a linear map, you can fold it into the neighboring weight matrices so it costs you almost nothing at runtime. The reported result is a 93.3% reduction in cache size and about 5.8 times the generation throughput, with quality that is, by their measurements, better than standard multi-head attention rather than merely close to it. And then watch how it spreads. That technique appeared in an open paper with open weights, and roughly a year later you find it in Kimi K2, in GLM5, in Mistral Large 3. Different labs, different countries, same compression trick, because the paper and the code were both there to read. The lag from publication to industry standard, for a serving optimization with a working implementation attached, is now about 12 months. Making the cache smaller is one half, the other half is managing it, and the two most important ideas that were both borrowed, more or less directly, from operating systems written decades earlier. The first is paged attention. The naive way to serve requests is to reserve a contiguous block of memory for each one, sized for the longest reply it might produce. Almost every reply is shorter than that, so most of the memory you reserved is never touched. Measurements at the time found that only a fifth to a bit over a third of the reserved memory was doing anything useful, so the fix is the same one operating systems reached for in the 1960s. Stop insisting on contiguous memory. Break the cache into fixed size pages, keep a table mapping logical positions to physical pages, and let a sequence's cache be scattered anywhere. Utilization goes to nearly all of it, and you can suddenly hold many more conversations in the same card. The second is prefix reuse. If two requests begin with the same text, and in practice enormous numbers of them do, because they share a system prompt or a document or the earlier turns of the same conversation, then the keys and values for that shared beginning are identical. Computing them twice is pure waste. RadixAttention organizes the cache as a prefix tree, so conversations that share an opening share the stored computation for it automatically, with a least recently used policy deciding what to evict. In 2024, this crossed a line that engineering optimizations do not usually cross. It became a product you can buy. Prompt caching appeared on the commercial interfaces with its own price. Send the same prefix again and it costs a fraction of the normal rate. When it launched, the discount was around half. By 2026, the cached rate is roughly a tenth of the uncached rate, which means the difference between an application that reuses its prefixes and one that does not is now nearly an order of magnitude on the invoice. That matters most for the workload that is growing fastest. An agent loop resends its whole accumulated history on every turn, so it is almost the ideal case for reuse. But naive caching is per machine, and the next turn frequently lands on a different machine, so the cache is not there. On a study of 610 real coding sessions, sharing cached prefixes across the fleet rather than per machine moved the hit rate from 1.7% to 92%. Same model, same requests, the difference was entirely in where the cache lived. This next one begins as a bug report and ends up as a component of modern architectures, which is a trajectory worth watching in full. In 2023, a group was trying to run a model over a text stream that never ends, like a chat that goes on for days. The obvious approach is a sliding window. Keep the most recent few thousand tokens and throw away the rest. It does not work. The moment the very first tokens fall out of the window, the model's output collapses, not degrades, collapses into fluent nonsense. And that is strange because those first tokens were usually something like a system prompt or the word they should not be load-bearing. So they looked at the attention maps, and there it was. Across essentially every layer and every head, a large share of the attention mass was being dumped on the first few tokens, regardless of what those tokens actually said. The models had all independently learned to do this, and nobody had told them to. The explanation is a consequence of the softmax, and once you see it, you cannot unsee it. Softmax is forced to output weights that sum to 1. It has no way to say nothing here is relevant. So when a head has nothing it wants to look at, it still has to put its weight somewhere, and the cheapest place to put it is a token that every position can see, and that carries almost no meaning. The first token is visible to everyone under causal masking, so it becomes the designated dumping ground. It is not a bug in the model. It is a release valve the model had to invent because the softmax gave it no way to abstain. The immediate fix is almost embarrassingly simple. Keep the first 4 tokens permanently, no matter how far the window has slid. 4 tokens, that is it. With those retained, a windowed model runs stably over millions of tokens. Same weights, no retraining, just do not throw away the drain. And then the idea graduated. If the model needs somewhere to put unwanted attention, do not make it improvise one out of a real token. Give it one. August 2025, when OpenAI released open weights, the architecture included a learned bias term added to the denominator of the softmax, 1 per head. That term is a legitimate off-ramp. The weights no longer have to sum to 1 across the actual tokens, which means a head can genuinely say this time, none of these. A pathology observed in an attention map in 2023 became a trained parameter in a shipping model 2 years later. Have been making attention cheaper to run. Now we have to deal with a different obstacle because none of the efficiency work in the world lets you use a longer context if the model has no idea where anything is. Remember from the last video that attention is order blind. It is a weighted sum, and a weighted sum does not care what order you hand it things in. Position has to be injected separately. The original paper did that by adding a fixed pattern of sines and cosines to the input embeddings. It works, but it has a flaw that only shows up when you try to go long. The model learns the positions it saw during training. Ask it about position 10,000 when it only ever trained to 512, and it is being asked about a region of the input space it has never encountered. The idea that replaced it is called rotary position embedding, and it is one of those constructions that feels inevitable once you have seen it. Take the query and key vectors and treat their dimensions as pairs, each pair being a point on a plane. Now rotate each pair by an angle proportional to the token's position. A token at position 1 gets a small rotation. A token at position 500 gets a large one, and different dimension pairs rotate at different rates, fast at one end, slow at the other. The point of doing that is what happens when you take the dot product. Rotating 2 vectors by the same amount does not change the angle between them. So when a query at position m meets a key at position n, everything cancels except the difference, m minus n. You put absolute positions in, and relative positions come out of the arithmetic on their own. No extra parameters, no learned position table, no additive term. And because the frequencies decay smoothly, the influence of a token naturally fades with distance, which is a reasonable prior for language, and it happens for free. The history of the idea is as interesting as the idea. It was worked out by Jianlin Su and first written up in Chinese on his own blog before it existed as a preprint in English. The preprint went up in April 2021. By 2023, it was in essentially every major open model and several closed ones. And the peer-reviewed version of that paper was published in February 2024, which means that for nearly 3 years, the position encoding underneath most of the field was a document that had not formally been through review. Everyone who adopted it cited the unrefereed version because the code worked and the models were better. That is not a criticism of anyone, it is just what the actual mechanism of adoption looks like in this field. So now everybody has rotary embeddings, and everybody has models trained at 2,000 or 4,000 tokens, and everybody wants 100,000. Retraining from scratch at that length is not affordable. So the question becomes whether you can take a model trained short and stretch it, and the answer to that question was worked out over about 3 weeks in the summer of 2023, partly in papers and partly on a message board. It starts in June 2023 with a short paper from Meta called Position Interpolation. The natural thing to try is extrapolation. Just feed in position 8,000 and hope the rotations behave. They do not. The paper's finding is blunt. Extrapolation produces what they call catastrophically high attention scores, because you are evaluating a rotation at an angle the model has never been calibrated for, and the result destroys the distribution. So instead, interpolate. If your model was trained to 2,000 and you want 8,000, divide every position index by 4. Position 8,000 is now presented to the model as position 2,000, and every position in between lands somewhere it has seen before. You are not asking the model to imagine a place it has never been. You are asking it to look more finely at a place it knows, and it works with a small amount of fine-tuning. 2 days later, a user on the local language model board on Reddit posts something better, with the comment that they derived the formula during lunch. Observation is that position interpolation squeezes every frequency by the same factor, and that is wasteful because the high-frequency dimensions are the ones that encode fine-grained local position, and squeezing those blurs exactly the information the model most relies on nearby. So rather than scaling the positions, change the base of the frequency series itself. That spreads the interpolation unevenly, mostly onto the low-frequency dimensions that handle long range, and it leaves the high-frequency ones nearly untouched. And unlike interpolation, it produces a usable model with no fine-tuning at all. A day after that, a different user posts a dynamic version, which adjusts the scaling as the sequence grows rather than fixing it in advance, so short inputs are not degraded by a setting chosen for long ones. Out 3 weeks later, the whole thing is merged into Hugging Face transformers with both usernames in the code comment, a production feature in the most widely used library in the field, credited to 2 anonymous forum posters 3 weeks after a lunch break. And then the thread became a paper. Yaren takes the insight and makes it principled. Divide the dimensions into 3 regimes by wavelength. The high-frequency ones, whose full cycle fits well inside the training window, are left completely alone. The low-frequency ones, which never complete a cycle even at training length, are interpolated. The ones in between are blended. And then it adds a second correction that the forum posts had not caught, which is that stretching the context changes the average size of the attention scores, so the softmax needs its temperature adjusted to compensate. With those 2 pieces, Llama 2 goes to 128,000 tokens in about 600 training steps. Would be tidy to say that this was a stopgap that native long context training later made obsolete. That is not what happened. Post hoc scaling of this kind is still shipping in 2026 in Gemma 3 in the open AI weights in QN. Turned out to be cheap enough and good enough that it stayed. Let us put dates on the race, because the shape of the curve is not what people usually assume. GPT-3 in 2020 had a context window of 2,048 tokens. In March 2023, GPT-4 arrived with 8,000 and a variant with 32,000. 2 months after that, Anthropic put 100,000 on Claude, which at the time sounded absurd, roughly a novel in one prompt. By late 2023, 128,000 and 200,000 had become the numbers you competed on. Then in early 2024, Gemini 1.5 went to 1 million, and later that year, 2 million became generally available. Through 2025 and into 2026, 1 million tokens stopped being a headline and became a checkbox. That is a factor of roughly 500 in 5 years, and because attention is quadratic, it is a factor of roughly 250,000 in raw attention work, which is only possible because of everything in the previous chapters. Curve is the visible output of all that invisible engineering. But the curve is not a straight line upward, and the 2 places it bends are more informative than the places it climbs. OpenAI shipped 1 million token window in April 2025, and then their next generation came back down to 400,000, with the larger window only returning later. That is a regression publicly in a headline specification, which companies do not do casually. Google's peak is older than most people think. The 2 million window shipped in June 2024. The models that came after it are back at 1 million. Both of those bends point at the same thing. If a longer window were straightforwardly better, and you had already demonstrated you could build one, you would not walk it back. You walk it back when the extra length costs real money to serve and is not delivering proportional value to the people using it, which raises the question the whole industry spent 2024 and 2025 learning to ask properly, and it is the subject of the next chapter. When a model says it has a million token context, what exactly is being claimed? The test everybody reached for first was called needle in a haystack. Hide a specific sentence somewhere in a very long document, ask the model to retrieve it, and vary both the length of the document and the depth at which the sentence is buried. Plot the results as grid. Green means found. Is a good test, and it is easy to run, and for about a year it was the number that got put on the slide. Problem with it was demonstrated most clearly by Anthropic about their own model in 2023. Claude 2.1 was scoring 27% on this test, which looked like a serious retrieval failure. Then they added one sentence to the prompt, telling the model to begin its answer with the most relevant quotation from the document. The score went from 27% to 98%. The retrieval had been working the whole time. What had been measuring was whether the model was willing to answer a question about a sentence that had obviously been pasted into an unrelated document, and a well-behaved model was declining to. The benchmark was measuring format compliance and being reported as capability. Harder benchmarks followed, and the picture they produced is consistently worse than the marketing. One widely used suite defines effective context as the longest length at which a model still beats a strong short context baseline, and by that definition, of the models advertising 32,000 or more, only about half actually hold up at 32,000. In one round of evaluation, 3 separate models advertising a million token context measured effective at 4,000, 4,000, and 16,000. And then this is not only external critics. The labs publish the decay themselves in their own model cards if you read the tables rather than the headline. One of Google's own reports shows 58% at 128,000 tokens falling to 16% at a million. An OpenAI report shows 97% at the short end of its own supported range falling to 37%, and nobody is hiding this. It is simply that the number on the box is the window size, and the number in the table is the performance, and those are different numbers. The honest 2026 update is that this did improve. The point where performance falls off a cliff used to sit around 32,000 tokens. It now sits somewhere past 256,000, which is a real advance of nearly an order of magnitude. But the advertised numbers moved further and faster than the effective ones, so the ratio between what is claimed and what is delivered never actually closed. The most recent work reframes the problem in a way that makes the whole length-based framing look like the wrong axis. What determines difficulty turns out not to be how many tokens there are, it is how the confusable material is arranged. Take a set of near-miss distractors, things that look like the answer but are not, and scatter them evenly through the document, and accuracy across every model tested drops to 2% or below. Exactly the same distractors in exactly the same document and cluster them together in one region, and accuracy comes back to between 93 and 98%, same length, same content, only the arrangement changed. Which suggests the thing that degrades is not the model's reach. It is its ability to hold a discrimination steady while the competing candidates keep arriving. Everything up to here has accepted attention and tried to make it affordable. Now we follow the people who did not accept it. Their question was different. If attention is quadratic because every token looks at every token, what if a token looked at nothing at all, except a summary of everything that came before it? That is a recurrent neural network, which is the architecture attention replaced. a fixed size state, updated one token at a time, carrying the past forward, constant memory per token, linear time overall, no growing cache. It has exactly the properties you want for long sequences. Reason it lost is that it could not remember far back because the state gets overwritten, and that it could not be trained in parallel because each step depends on the last. The line that revived it starts with a piece of mathematics about how to compress a history optimally. The result, called high PPO, gives you a specific structured matrix that keeps a running approximation of everything seen so far, projected onto a basis of polynomials, updated online. It is not a heuristic, it is derived, and it turns out that if you initialize a state space model with that matrix rather than randomly, the memory problem largely goes away. That became S4 in 2021, and S4 walked into long-range arena, the benchmark that had humiliated every efficient transformer, and scored an average of 80.48 against the field's 59.37. Not a fraction of a point. 21 points above the whole field, and it did the thing the benchmark had been built to be impossible. PathX, the 16,000 pixel task where every attention-based model of every kind had scored at chance, S4 solved at 88.1. Remember when that table was published, the interpretation was that the task was simply too hard. It was not too hard. It was too hard for that family of models. The catch with S4 is that its state update is the same for every token, which means it cannot decide that one word matters more than another. Mamba in 2023 fixed that by making the parameters of the recurrence depend on the input, so the model can choose to remember this token and forget that one. That is the selection mechanism, and it is what closed most of the remaining language modeling gap. But making the recurrence input dependent, the mathematical trick that let S4 be computed as a convolution, so Mamba also had to come with a hardware-aware parallel scan, written to keep the state in fast memory and never write it out, which is, you will notice, the FlashAttention argument arriving in a completely different neighborhood. And the result has the shape you would want. A transformer's cache grows by one column for every token forever. Mamba's state is a fixed size block that gets overwritten. Generation throughput reported at around 5 times a transformer of comparable size, with no growing cache to stream. On paper, this looks like the end of the story. It is not, and the next 2 chapters are why. In 2024, the Mamba authors published a follow-up, and the interesting part of it is not the speed improvement. It is a proof that the 2 roads we have been following, the attention road and the state space road, are not 2 roads. The claim is called the structured state-space duality, and stated plainly it is this. Take a selective state-space model and simplify its transition so that instead of a full matrix, it is a single scalar multiplying the identity. It out what that model computes across a whole sequence as one matrix rather than as a recurrence. What you get is linear attention with a decay mask. The 2 families are not analogous. Are the same computation written in 2 notations by 2 communities who spent several years unaware of it. The identity at the center of it is compact enough to say out loud, the sequence transformation matrix M equals L, element-wise multiplied by C times B transpose. C times B transpose is the score matrix, the same object as query times key transpose in attention. L is a lower triangular matrix whose entries are the cumulative products of the decay factors, which is simultaneously the causal mask, because it is 0 above the diagonal, and the forgetting curve of the recurrence, because the entries shrink as you move away from the diagonal. One matrix doing both jobs, attention sees a mask. The state-space model sees decay, they are the same number. And this is not a philosophical observation. It is a compiler. Once you know the object is a matrix with structure, you can compute it the way you compute matrices, which means in blocks on the tensor cores, using the same machinery a decade of attention optimization has already built. The diagonal blocks get handled as quadratic attention within a chunk, and the off-diagonal blocks get handled by passing the recurrent state between chunks. Chunkwise algorithm is 2 to 8 times faster than the original scan. And it comes directly from having recognized what the thing actually was, understanding pay to speed up. It also reframes the entire debate. The question was never attention versus recurrence. It is a question about what happens between tokens, and there is a spectrum. At one end, an unbounded cache that keeps everything and pays quadratically. At the other, a fixed state that keeps a compressed summary and pays linearly. Everything in this video sits somewhere on that line, and the argument is about where. Which brings us to the rebuttals, and they deserve as much time as the claims did because they are the reason nobody shipped a pure state space language model at frontier scale. The first hint arrived before Mamba even existed. The H3 paper in 2022 was trying to close the gap between state space models and transformers, and along the way it ran an experiment that turned out to matter more than the architecture it was proposing. Took a state space model and added just 2 attention layers, not a hybrid design, just 2 layers dropped in, and that hybrid beat a full transformer of the same size 2 layers. Which tells you that whatever attention is contributing, most of it is available very cheaply, and also that it is not optional. The second is a paper called Zoology, which did the diagnostic work properly. It took the remaining perplexity gap between gated convolution models and attention and asked token by token where the gap actually lies. Answer is that 82% of it is a single skill called associative recall. That is the ability to notice that a particular pairing appeared earlier in the text and reproduce it when the first half shows up again. A document says that the project codename is Hawthorne, and 2,000 tokens later says the codename is, the model has to produce Hawthorne, and the demonstration they built out of that is devastating in its simplicity. On that specific task, an attention model with 70 million parameters beats a gated convolution model with 1.4 billion, 20 times the parameters losing on one skill. The third result is not empirical, and that is what makes it decisive. A paper called Repeat After Me proves that a model with a fixed size state can not copy arbitrary length strings. The argument is essentially counting. Reproduce a sequence you have never compressed. You must have stored enough information to distinguish it from every other sequence of that length, and a state of fixed size can only distinguish a fixed number of things. Feed it a longer string and you exceed the capacity always. Is not a limitation of current training or current initialization. It is a limitation of the shape. Attention does not have it because attention's cache grows, so it can always go back and read the original. So the trade is now precisely characterized. Constant state buys you linear time and a cache that does not grow. What it costs you is exact recall of things you did not know would matter when you saw them. And for a chatbot summarizing a paragraph, that cost is invisible. Auto reading a codebase and being asked what a function was called 400 lines ago, it is the entire job. So the field did the sensible thing, which is also the boring thing. Nobody shipped pure attention and nobody shipped pure recurrence. They shipped mixtures, and the interesting question stopped being which architecture and became what ratio. But in 2024, went with 1 attention layer for every 7 state space layers. Minimax's first large hybrid went the other way, roughly 7 linear layers for each full attention layer. Granite 4.0 used 9:1. And through 2025 and 2026, a convention emerged around 3:1, which is where you find QN3 next, QMI-linear, and QN 3.6. 3 cheap layers, 1 full attention layer, repeated. Labs arriving at similar answers independently, which usually means the answer is being set by something real rather than by fashion. And notice what that shape is: a small number of layers that can look at everything exactly, interleaved with a majority of layers that carry a compressed summary cheaply. Which is structurally the same answer Chapter 4 ended on, when the local sliding window survived alongside full attention rather than replacing it. The field converged on the same shape twice, from 2 directions that had nothing to do with each other. Dow, who wrote both FlashAttention and Mamba and is therefore about as well positioned as anyone to have a view, has said as much directly. His expectation is not that linear layers replace attention. It is that they are used in conjunction with it. person who built the fastest attention kernel in the world and the leading alternative to attention thinks the answer is both. And the honest counterweight, which does not usually get quoted alongside the ratios, many Macs adopted linear attention in one generation and reverted to full attention in the next, publicly. Their stated reasons were that the linear variant hurt on reasoning tasks and on multi-turn accuracy, the two things that matter most for the way models are actually being used in 2026. That is one lab, one data point, and it should not be read as a verdict on the whole approach. But it is a lab that built the thing, shipped it, measured it in production, and went back. That is worth more than most benchmarks. Which leaves the last movement, and it is the biggest architectural story of the period. Sparse attention came back. And the obvious objection is that we spent chapters 2 and 3 watching sparse attention get benchmarked into the ground, so what is different this time? Things are different, and they are all worth naming precisely. The first generation of sparse attention was mostly applied to a model after the fact or with a pattern fixed by hand. This generation trains the sparsity from the start, so the model learns around it rather than being retrofitted with it. The first generation was designed on a whiteboard and then handed to the hardware, where the irregular memory access patterns ate the theoretical savings. This generation is designed against the memory layout of the accelerator first, so the speed up on paper is the speed up you get. And the first generation was aimed at training. This generation is aimed squarely at decode, where we establish the bottleneck actually lives. The clearest example is NSA from February 2025. It runs 3 paths in parallel. One compresses blocks of the past into summary tokens, so the model has a coarse view of everything. One selects a small number of blocks to attend to at full resolution, chosen by the model itself. One is a plain sliding window for local detail. A learned gate decides how much of each to use per query, and it reports 11.6 times faster decode at 64,000 tokens, which is expected. What is not expected is that it also beats full attention on quality benchmarks. Not matches, beats. The interpretation is that forcing the model to select is a useful constraint, not just a cheaper one, because a model that must choose what to look at learns to look at better things. MoBA appeared 2 days later from a different lab, with a different mechanism reaching the same place. Divide the context into blocks and let each query route itself to the top few blocks, exactly the way a mixture of experts layer routes tokens to expert. It ships with a switch that lets you flip any given layer back to full attention, which is a very practical piece of engineering, and it was already running in production behind a consumer product. Then in September 2025, DeepSeek shipped their version in a released model rather than a paper demo, a small, cheap indexer scores which tokens matter for each query, and then full attention runs over only the top 2,048 of them, no matter how long the context is. The part that tells you it was real is the pricing. On the day the model shipped, the interface price was cut roughly in half. You do not have your own rev per token as a marketing gesture. You do it because your serving cost genuinely fell. The caveat stated plainly because it is the one thing that usually gets left out. That indexer still has to score every token against every query, which means the quadratic term has not gone anywhere. It has been made cheap, running at low precision with a tiny number of heads, but it is still there. The honest description is that the coefficient in front of n squared was reduced by a very large factor, not that the n squared was removed. 4 labs across about 18 months arriving at the same design. Learn what to attend to at block granularity with a cheap scorer in front and exact attention behind it, written against the memory hierarchy. When independent groups converge that tightly, it is usually because the constraints are doing the designing. 10 years, and the question we started with, was the quadratic problem solved? The answer depends entirely on which quadratic problem you meant, and the two of them have had very different decades. The compute problem is, for practical purposes, handled, not by any single breakthrough, and not by an approximation that replaced attention, which is what everyone expected in 2020. It was handled by a stack of unglamorous engineering. Stop writing the matrix down. Share and compress the cache. Page it like an operating system. Reuse the prefixes and bill for the difference. learn which blocks to read and skip the rest, put a small number of exact attention layers among a majority of cheap ones, and none of those is elegant. All of them are in production. The bill still says n squared somewhere in the fine print, and almost nobody pays it. The learning problem is not solved, and I do not think it is close. Making attention cheap to compute does not make it easy to learn. A model with a million token window has to learn useful relationships among quadratically many pairs of positions. From training data in which genuinely long documents that require genuinely long-range reasoning are rare, that is a data and optimization problem, and no kernel fixes it. It is exactly what the effective context measurements keep finding, and it is why the newest results point at the arrangement of distracting material rather than at length. The reach was extended. The discrimination did not keep up. Which produces a conclusion that sounds like a joke and is not. The most effective long context technique available in 2026 is not using long context. Break the task into pieces that fit comfortably. Clear out what is until instead of letting it accumulate. Retrieve what you need rather than pasting in everything you might need. Never pay for the same tokens twice. The people building the most reliable systems on top of these models are, overwhelmingly, the people being disciplined about how much they put in the window, not the people filling it. And after all of it, look at what is still at the center. 10 years of approximations, benchmarks, kernels, caches, rotations, state spaces, and learned sparsity. And the thing all of it is arranged around is the same line of arithmetic we drew in the last video. Query times key transpose divided by the square root of the dimension through a softmax times value. Nobody replaced it. What changed is everything around it, and that turns out to be the more interesting story because it is the one where you can see the field actually thinking. Thanks for watching.